And good evening, AP Physics students. Mr. Curson coming at you here, talking about a little thermodynamics today. Thermodynamics. And as always, we start out with laws, right? When we're studying new topics. Laws being ideas that have been discussed by many scientists over time and be shown to be true in the experiments we've observed. So, Thermodynamics, chapter 15, begins with the first law of thermodynamics. And it sounds complicated and it looks brand new. I always think of the first law of thermodynamics as simply a statement of conservation of energy. But anyway, let's talk about it. The first law of thermodynamics looks like this. And it states that the change in internal energy of a gas, okay, is equal to the heat gained or lost by it plus the work done on it or done by it. Now, to me, this just kind of makes sense. I have a gas that has some energy, and if I add heat to that gas, it would increase its energy. On the other hand, if this gas did some work and energy left the system, the internal energy of the gas would decrease. So I always try not to get too caught up in definitions in this law and just think about energy. What's happening to the energy of the gas? Now, why is this important? Well, if we have a gas that's in a cylinder, say that has a piston like this, we can get this gas to do work for us, right? So a steam engine, a locomotive, your car engine, right? If we can all think about those things in terms of thermodynamics, heat gained and work done, we can describe the physics of that situation, which, as you know, engines and generating power are important in the world we live in. So, one quick warning here. Your book uses a negative sign here and defines the work done to be by the gas, whereas the AP equation sheet uses a positive sign here and then defines it to be work done on the gas. Now this can get really confusing, so I just put all conventions inside and say, hey, if energy's exiting the system, it should be negative. If energy's entering the system, it should be positive, all right? So if I heat up a gas, I add heat, that should be positive. If I take heat away, that should be negative. If the gas does work, all right, that's energy leaving the system. If work is done on it, that's energy entering the system, okay? So internal energy, heat, and work. Now, I don't do this very often in physics, but there's some vocabulary you're going to need to know. All right? Now, physics usually isn't a whole lot about vocabulary, but boom, here it is. Table 15.1, if you're following along at home, on page 412, you should memorize this table, okay? Or at least memorize the terms in it. And let's go over them here really quick. And when I say memorize, you know what? They should make sense if you kind of think about it. For instance, an isothermal process, a gas that undergoes an isothermal process has the same temperature. Iso, same, thermal, temperature. So remember that in an ideal gas, temperature and internal energy are synonymous terms. All right? Temperature is a measure of the average kinetic energy of the particles in the gas, and for ideal gases, that's the only type of energy that they have. Isobaric, think of a barometer, all right? What's a barometer measure? Pressure. An isobaric process happens at the same pressure. Isovolumetric process, also called isochoric, occurs at the same volume. In those processes, no work is done. And adiabatic has no heat flowing into or out of the gas, okay? So Q is 0 for adiabatic. Now, when describing these gases that are in a cylinder, We sometimes describe them, so I might describe a gas that looks like this with a PV diagram. A PV diagram is simply a graph of the pressure and volume that the gas is influenced by. And we call such a diagram a PV diagram. And the reason these are important is you can calculate how much work is done by a gas by multiplying the pressure of the gas times the change in volume. All right, if you think about the units here, pressures in newtons per meter squared times meter cubed, oh, that's a newton meter, and that's a joule. So again, if you think about work being force times distance, if this gas exerts a pressure up and exerts that force through a distance, that gas can do work. And we're really interested in that because we like it when we can design machines that do work for us. Speaking of work, let's get down to it and do some work on problem number 2. So in problem number 2, it states that we have a gas, an ideal gas, that is isobaric and undergoes an isobaric process, and the initial pressure is equal to the final pressure, and that pressure is 1 atmosphere, right? So we can think about on a PV diagram of pressure being like this, same pressure. Now we're also told that the initial volume of the gas is 12 meters cubed, and the final volume of the gas is 18.2 meters cubed. Okay? And part A of this question asks us to calculate how much work is done by this gas. Okay? So P times delta V here, if this is VI and this is VF, okay, is the work done by this gas is P times delta V. And to get this work in joules, I'll want to make sure my pressure is in pascals. So 1 atmosphere, 101.3 kilopascals, or 101,300 pascals, times change in volume would be 18.2 minus 12.0. And I would get the amount of work done by this gas, which is about 628,000 joules. Again, this is work done by the gas because the gas is expanding, pressing out on that piston, and doing work for us. All right. Okay. So we've calculated the work done by this gas. By the way, since work is P times delta V, you can also think of this area under a PV curve as being equal to the work. All right, and we're going to use that a lot later in the chapter. So area underneath a PV curve is also equal to the work done, since the work is P times delta V. Okay, part B says, what does part B say? Part B says, calculate the change in internal energy of the gas. And we're also told in the problem that in this process we add 1,400 kilocalories of heat during the process. Okay, so I know how much work is done by the gas. I know how much heat is added. I just need to find the change in internal energy of the gas. So if I convert this kilocalories into joules, I'm going to find that this heat done, again, we would multiply here by 4.186 joules in 1 calorie. And I would get this is equal to 5,860,000 joules. And of course, since this work is energy leaving the system, I would subtract off the work done by the gas, and I would get a change in internal energy of 5,232,000 joules. All right. So much of the heat that we added went into increasing the internal energy or the temperature of the gas. All right, nice work, physics students. Make sure you keep the first law of thermodynamics in mind and its statement of the law of conservation of energy. Make sure you remember your vocabulary here for the chapter. And your inspiring story of the day has to deal with Saturn's rings and Saturn's moons being made out of the same material. Interesting article in Sunday's paper about Saturn's moons and its rings. All right, nice work, AP Physics students. We will see you tomorrow.